This is Samuel Alwani again. This is lecture 2 in power electronics, and I'm going to talk about half-wave uncontrolled rectifier. And for this purpose we will be using the power diode shown here. And the ideal characteristic of a power diode is, if this is the IV characteristic of the power diode, then whenever we apply a positive voltage across the diode terminal, then the diode will conduct, meaning a current will flow through the diode. The diode behave as a closed switch and it's on. When there is a negative voltage applied across the diode will block this voltage, meaning that it will behave like an open switch and it's gonna be off. This is the ideal case for a power diode. For non-ideal case, for silicon diode for example, when the voltage across the diode is positive 0.7, the diode starts conducting, and this is like a threshold voltage level to make the diode turns on. And during off, the diode will block certain amount of negative voltage, and when it reached to a certain level, the diode will break down and it will behave like a short circuit, and this voltage is called breakover voltage of the diode. So this is for a non-ideal case. We will consider the ideal diode in our calculation for half-wave uncontrolled rectifier. So the first type of half-wave uncontrolled rectifier is half-wave rectifier with resistive load, R load, and the circuit diagram will be, this is the voltage source, this is the diode, and this is the load resistance. V out, which is the output voltage across the resistance, and this is the voltage of the source. If I want to graph the voltage waveform of the voltage source, it will be like that. This is the maximum value of the voltage. This is T, the period. And if I want to find the output voltage across the resistance, when the voltage across the diode is positive, meaning this half cycle, the diode start conducting, meaning that there is no voltage drop across the diode. All the voltage will appear across the resistance, so this will appear across the resistance for this positive half cycle. And when the voltage turns to be negative, the diode behaves like an open circuit, so it will be an open circuit. Then the voltage across the resistance is 0, and since this is a resistive load, the current will take the voltage shape waveform. So this is IR, this is V output, and if I want to find the voltage across the diode, when the diode is on, meaning that there is no voltage drop across the diode, the voltage is 0, when the diode behaves as an open circuit, an open switch, the negative voltage will appear across its terminal. So now we need to calculate the amount of power transferred to the resistor and to measure also the power factor and to measure total harmonic distortion and other things. So first of all, since this the voltage appear across the resistance is positive all the time, despite the fact there are some zero appears in the signal. So as we see here, the source current is equal to the current that moving through the diode is equal to the load current. So if I want to find the DC component of this signal, either for the voltage or for the current, then I have to find the average value for these two signals over the whole period, which is t. So since this is a sinusoidal signal, this will be pi and the period will equal to 2 pi. So I will find the average, the value of the DC voltage, by integrating the signal of the voltage source, which is Vt as a function of time, from 0 to 2 pi. This is how to find the average value. So as we know that V source as a function of time is equal to V maximum sine omega t. So the voltage DC, or the average value of the voltage at the load, is equal to 1 over 2 pi from 0 up to half of the period, which is pi. Because from pi up to 2 pi, the voltage, the value is 0. So I will plug in the value of the Vt, which is sine omega t dt, plus 1 over 2 pi from pi up to 2 pi, 0 dt. So I'll ending up analyzing this term. So VDC will equal to 1 over 2 pi. Take V maximum out of the integral since it's a constant. Then integrate sine omega t, which is minus cosine omega t from 0 to pi. Then V maximum over 2 pi. Cosine pi is minus 1 multiplied by minus 1. It's 1. Minus is plus. Cosine 0 is 1. So it will gives me V maximum over pi. So this is the DC component of the signal, which is V maximum over pi. And the current IDC is simply the DC voltage over the resistance, and the DC voltage is this, so it will be V maximum over pi multiplied by R. So this average DC current is the same average DC current drawn from the source. Now if I want to find the apparent power, the power factor of this converter, it's the active power drawn by the load divided by the apparent power drawn by the load. And we know that the active power is simply the RMS voltage multiplied by the RMS current in the output side divided by the RMS voltage of the source multiplied by the source RMS current. And what are actually the meaning of RMS current and RMS voltage? So aside, I will explain what is the meaning of RMS. RMS is stand for root mean square. It's actually the effective current in the AC signal that will produce the same amount of power that a DC current will produce. What I'm saying is, if I have a battery connected to a resistor, the current that is flowing through the resistor is simply the voltage divided by the resistance, and this current will produce this amount of heat dissipated on the resistor. So what if I replaced this DC source with an AC source? How much AC current we need that will produce the same amount of power that this DC current produces? So it's called the effective value. As we know, the current in this AC circuit is a sinusoidal current. Its average value is 0. If we want to find the average value over one period, it will be equal to 0. But the RMS value of the current is like taking the absolute value of this current. So this signal will become like that, and then square the signal and take the root of it. So this is, so now why it's called root mean square value, why it's called RMS? It's simply by finding the equivalent current that will be as effective as the DC current here in this equation. Now if I want to find the effective value of the current that will produce the same amount of heat as this DC current produced in the first circuit, then I have to say that the average power in the AC circuit is 1 over T integral from 0 to T. We said earlier that it's VT IT dt, or I can say it's 1 over T integral from 0 to T I of t squared multiplied by R dt. So this AC power average is equal to 1 over T. Take the R outside of the integral since it's a constant. So it's from 0 to T I square as a function of time dt. So if I want to find the effective value of the current that will produce the same amount of power, then the AC power produced in the resistor is equal to the DC power, and I would plug in this equation here, so it will be R over T integral from 0 to T I square T dt equal to the DC current here is equal to I DC, or effective value, multiplied by the resistance, and this is square. Then we see here a resistor that goes with this resistor. Then IDC, or effective square, which is this one, will equal to 1 over T integral from 0 to T I square T dt. So now I will take the square root for both sides, and I get the effective value of the AC current that will produce the same equivalent amount of heat into the resistor as a DC current. So this is the formula. So this is why they call it root mean square, because we are taking the square root of the mean of the square of the signal here. So this is called IRMS, and the same goes for the voltage. RMS, it will equal to the square root of 1 over T from 0 to T V square as a function of time dt. So if we go back to our half-wave rectifier here, we found the DC voltage and DC current here in this equation and in this equation. Now we want to find the power factor, and the power factor allows us to measure the quality of conversion from AC to DC. So I need to find the VRMS and IRMS in the load side, and VRMS and RMS in the source side. So just apply this RMS formula. So now to find the source RMS voltage, I will take the square root of 1 over 2 pi from 0 up to 2 pi V maximum sine omega t squared d omega t. So this will equal to 1 over 2 pi, take the V maximum square outside of the integral, so from 0 up to 2 pi sine square omega t d omega t So now it's V maximum square over 2 pi from 0 up to 2 pi. Sine square omega t has no definite integral, so we will use trigonometric identity, which is 1/2 minus cosine 2 omega t over 2 d omega t. So now I can get V maximum square over 2 pi. I will have half multiplied by 2 pi, so it's like 2 pi over 2 minus 0 for the first part. For the second part I will add a minus cosine 2 omega t over 4. It will be cosine 2 multiplied by 2 pi, which is 4 pi, which is 1. So it will give me 1 over 4 minus cosine 0 is 1. So it will give me 1 over 4. So this will cancel with this, so it's 0, this term. The only term remain is this one. So Vs RMS will give me V maximum square over 2 goes with the 2, the pi goes with the pi, so over 2. So the final answer is V maximum over rho 2. So this is the RMS value of the source voltage, and the RMS value of the current is going to be I maximum over rho 2. So we found the source voltage and current RMS. Now to find the output RMS voltage in the half-wave rectifier, so we'll do the same thing. It's gonna be V maximum square over 2 pi integral from 0 up to pi, since from pi up to 2 pi it's 0. So I'm gonna have half minus cosine 2 omega t over 2 d omega t. This will equal to V maximum square over 2 pi. First part is pi over 2 minus 0 minus cosine of 2 pi is 1 divided by 4 minus also 1 over 4. So this term is 0. This pi goes with this pi. We have left V maximum square over 4. Multiply this 2 by this 2. So we get V maximum over 2. So this is the output RMS voltage of the half-wave rectifier. Also the output RMS current of the half-wave rectifier will be I maximum over 2. So if I want to find the power factor it will be V maximum over 2 multiplied by I maximum over 2. This is the active power. So since the IS is equal to IR, they both have the same RMS value, which is I maximum over 2. So it will be V maximum over root 2 multiplied by I maximum over 2. So this one goes with this one. So I will get 1/2 divided by 1 over root 2. And this will gives me 0.707. So this is the power factor of a half-wave rectifier with resistive load. This is an example for a half-wave rectifier. Let's say we have a half-wave rectifier and the voltage source applied to the load through the diode is 170 sine 377t. So we have a load resistance of 12 ohms. From the Vs we can find that V maximum here is equal to 170 volts. Omega is equal to 377 radian per second from here. So first they asked to find the average current. So the average DC current is V maximum over by R. So it's 170 divided by pi multiplied by 12. And this tends to be 4.51 amps. They asked the RMS current. The RMS current, as we know, is the output RMS current equal to the source RMS current, which is equal to V maximum over 2, so 170 over 2 multiplied by R, so multiplied by 12. This will gives me 7.08 ampere. Then they ask the apparent power. The apparent power is the source RMS value multiplied by the output RMS value. So the RMS value of the voltage on the source side is 170 over root 2 multiplied by 7.08, and this will equal to 851.5 volt ampere. And finally they want us to find the power factor. So the power factor is the average power divided by the apparent power. The average power is 170 over 2 multiplied by the current 0.08 divided by S, which is 851.5, and this will equal to 0.707. As we know, for any resistive load half-wave rectifier, the power factor always doesn't change.